All right, welcome back. So we're going to do yet another way to figure out the change in enthalpy for a reaction. And so this time what we're going to do is we're going to be breaking bonds and reforming them. Just so you're aware that all of the methods that we're using for figuring out change in enthalpy, they will all get the same answer, although they get to it in a different way. First thing you need to be aware of is that whenever we break a bond, we have to put in energy to break that bond because it's more stable to begin with. Whenever we form a bond, it's going to release energy. So imagine if you have two individual atoms, the height of my body is energy. If you are two individual atoms, you're going to have high energy, but when you form a bond, you're going to drop in energy, and that energy is going to be released. But the opposite is true as well. When we break a bond, we have to input the same amount of energy, and we call that bond energy. Now, how do we work with this? Well, you're going to see on the next table, you're going to see a table that shows us all the different bond energies, but I want to focus on this equation right here. See how this change in enthalpy says it's the bonds broken minus bonds formed? And this is the first time in all of the change in enthalpies that we're dealing with where we're not dealing with the products first and then the reactants, because if you follow the sequence, in order to cause a reaction to go, you need to break all the bonds of the reactants and then you need to reform them. This formula, this sigma, means that you have to break all of the bonds. That n tells you how many bonds there are. Now the reality is the best way to do this is to try a problem, so we're going to do this right now. So we have this equation right now, and if you take a look, what I do is I try and write down all of the bonds that are existing. So if you take a look at H2, wouldn't that be an HH? And then we have F2, which is an FF bond. And then over here, you can see we have a coefficient here of 2, which means there's 2 of these HF bonds. Now, remember our overall equation is going to be the sum of all of the bonds broken minus the sum of all the bonds formed. So if I take a look here, I'm going to just write in the numbers here. So if I were to do the overall thing, I'd say the sum of bonds broken minus the sum bonds formed. Now, what do we have on the reactant side? I'm going to put a big parentheses around this here, but if we take a look here, we have HH, which is 432, so we're going to go 432 plus 154, and that's my reactant side. Those are all the ones we're going to break. Then we have to subtract 2, and again, we might want to put a big parentheses here, 2 times the HF, and the HF, if you look in the table, is 565. And when we do this all together, we're going to end up with 586 here, and we're going to subtract 1,130 here, and the overall change in enthalpy for the reaction is going to be equal to negative 544 kilojoules. Now remember, we had this conversation in class about whether it's kilojoules or kilojoules per mole. Kilojoules per mole is the best way to do it, but I also want to point out that the negative sign right here, this is a big deal because that tells you this is an exothermic reaction. Let's try another one. This one's a little more complex, and the way, again, I do this is I'll draw all of the individual bonds here. So it might help you to go like this. I have CH4, I'm going to draw CH4 here. And then I have 2 of these CLs, and I have 2 of these FFs. That is my reactant side. On the product side, again, I'm going to have a carbon in the middle, and if you want to, it does help to do it this way. I have 2 fluorines attached, and I have 2 CLs attached, and that kind of allows you to see what bonds you have between what things, and you can look at the table. And then we have 2 of these HCl's. Now again, let's write the equation. It's the sigma symbol is bonds broken minus bonds formed. 2 things you need to be aware of. It's also the coefficients, the number of moles of each of these, and that should be a sigma, and that should be on the inside of it. So it's all the way terrible the way I've just written it. However, what we can do is we can write, based on what the table is, all the different bonds. So if we take a look here, I'm going to make a big parentheses here to make it a little bit easier to see. But don't we have, if we put a hydrogen on the outside of each of these right here, wouldn't that indicate to us that we have 4 of these CH bonds we have to break, right? And then we also have 2 of the CLCLs. And I'm going to do this just because I don't want to be redundant with this. I'm going to actually just write in the values because I don't have a ton of space. So each of these CH bonds, if I look up here on the table, is 413. So I'm going to go 4 times 413, right? I'm just going to put that in parentheses to note they're together. And then I'm going to go, there are 2 times the ClCl, which if you take a look on the table here is 239. And then we have, so we're going to put all this together. And then we're going to have our FF is 154, and we have 2 of those FFs, which in this case is going to be 154. That's all on this side. I'm going to parenthesize this as well. Then we're going to subtract on the other side. We have 2 times the CF, which is going to be 485. I'm ignoring writing the kilojoules in here, but you should probably not do that. And I'm going to add that to 2 times the CF, CL2, sorry, which would be 339. And I'm going to add that to 2 times the HCl. So let's do the calculations on this. That's going to give me 1,652. So the overall change in enthalpy for this reaction is going to be equal to negative 64 kilojoules per mole. Now, that whole dead space right there was just me punching in numbers on my calculator, and by that I mean my phone. But what you want to be aware of is this. Probably the most important part of this, the entire part of this, is making sure that you know this right here. Like what is being formed and what is being broken apart. So you kind of have to draw the structures first and then add them all up at the very end. Now, I will say this. If you were to do the previous videos method of looking up in a table the change in enthalpy of formation of each of these things right here, and you took the products enthalpies of formation and subtracted the reactants enthalpy of formation, you would get this exact same number. So this is just another way of doing the same exact thing we've been doing before. The best way to get good at this is to practice on it. Hopefully this has been helpful. I'll see you in class.